this is our matrix A and this is our matrix B. So now you can write down B plus A. Okay, so now this is just one example for 2 cross 2 matrix. Now similarly that can be happen for any n cross n matrix, right? So this commutative law is coming from this, because of we have commutative law in real numbers, so that's why we can use it. Okay. So the second property is satisfied for that one. The third condition is existence of additive identity. The third condition is for existence of additive identity. For each 0 that is equal to 0 ij belongs to Mn, then for every a is equal to aij belongs to Mn. For a plus 0 that is equal to aij plus 0 ij, that is equal to aij in bracket aij plus 0 ij, that is equal to aij, that is equal to a. So this 0 element is actually nothing but the n cross n matrix which contains all the 0 elements, right? So whatever the size of your matrix, so that's why similarly we can prove that 0 plus a, that is equal to a. Okay, now next, the fourth condition, existence of additive inverse. Existence of additive inverse. For each a is equal to aij belongs to Mn, there exists minus a, that is equal to minus aij belongs to Mn, such that a plus minus a, that is equal to aij plus minus aij, that is equal to aij minus aij in bracket, that is equal to 0. Similarly we can prove that minus a plus a, that is equal to 0. Now so the first 5 condition for addition, one is closeness, that we already proved before to prove that 8 condition, and this 4 condition. So the first 5 condition for addition is already satisfied. Now next 4 condition for scalar multiplication. So closeness for the scalar multiplication we already proved, and next first condition is for distributive law, that let alpha belongs to R, then alpha into a plus b, that is equal to alpha into in bracket aij plus bij, that is equal to alpha into in bracket aij plus bij, that is equal to alpha into a plus alpha into b. So this distributive law is satisfied, alpha into a plus b, that is equal to alpha into a plus alpha into b. Next one is again distributive law for the scalars, alpha beta belongs to R, then alpha plus beta into a, that is equal to alpha plus beta into aij, that is equal to alpha plus beta aij, alpha aij plus beta aij, alpha aij plus beta aij. Now you can understand using this, it's quite difficult to say, but now using this property you can understand that how we prove that alpha plus beta into a, that is equal to alpha into a plus beta into a. And this condition is also quite easily satisfied, associative law, alpha beta into a, that is equal to alpha beta in bracket aij, that can be alpha beta aij in bracket, and similarly we can prove that alpha beta a, that is equal to beta into alpha a. So if 1 be the unit element of R, then for every a belongs to Mn, 1 into a, that is equal to 1 into aij, that is equal to 1 into aij, that is equal to a. So this all the 8 exams except the closeness for the addition and scalar multiplication we already defined, we already proved before to prove that these 8 conditions. So total number of 10 conditions we already satisfied by the elements of Mn. Hence this set Mn, that set of n cross n matrix on real numbers with the standard addition and scalar multiplication, is a vector space. Okay, so just try to understand how many conditions we have to satisfy for the vector space. Total number of 10 conditions, first 5 conditions are for addition and the next 5 conditions are for scalar multiplication. Okay, so just try to understand proper the using the definition we satisfied one by one each condition. Okay, so next example, question 3b. Determine whether the following spans the vector space R3 or not. V1 is equal to 2 minus 1 3, V2 is equal to 4 1 2, V3 is equal to 8 minus 1 8. V1 is equal, here we use one theorem that dimension of V is equal to n and S contains exactly n elements, then S is a basis for V. Okay, here we use one important theorem. That theorem says that if S contains exactly n elements and the dimension of V, here what is our V? V is equal to R3. What is our vector space? Vector space is our R3. Okay, so we know that dimension of Rn is equal to n in general, that we already know that dimension of Rn, that is equal to n. Okay, and here S is equal to means contains V1 V2 V3, exactly 3 elements. So if this situation happen, if dimension of V is equal to n and S contains exactly n elements, then S is a basis for V if and only if S is linearly independent or S spans V. Okay, so in that case, using that theorem, you can say that S is linearly independent and S spans V. These two statements are equivalent. These two statements are equivalent. In which condition? If the dimension of the vector space and the set S contains the exactly same number of element, right? The dimension of the vector space and the S contains have the same number of element, right? So the S contains same number of element, as such the dimension. So in that case the S is linearly independent and S spans V. These two statements are equivalent. So basically here we want to prove that or we want to check that these three vectors are spans R3 or not. But for that we check that these three vectors are linearly independent or not. That is enough using this theorem. Okay, so that's why we are doing that one, because it's a shortcut method. It's quite easy to check that these three vectors are spans R3 or not. Okay, so and to prove or to check that these three vectors is linearly independent or not, for that we use determinant method. To solve this determinant, if the value of determinant is equal to 0, we can say that these three vectors are not a linearly independent, and the value of determinant is not equal to 0, we can say that these three vectors are linearly independent. Okay, so here is three vectors: 2 minus 1 3, 4 1 2, 8 minus 1 8, that is equal to 2 into 8 plus 2. To solve this determinant, 2 into 8 plus 2 minus 1 into 32 minus 16, right? 4 into 8, that is 32 minus 16, plus 3 into minus 4 minus 8. Okay, that is equal to 20 minus 16 minus 36, that is equal to 0. Hence S is equal to V1 V2 V3 is not a linearly independent, where S is equal to, so the value of determinant we get 0. So the set S is equal to V1 V2 V3 is not a linearly independent, where S spans R3. Okay, S spans R3. Two 2 2 0 0 3 0 1 1, the next three vectors. Again we use this determinant property. 2 2 2 0 0 3 0 1 1, 2 into minus 3 minus 2 into 0 plus 2 into 0. So basically we get minus 6, which is not equal to 0. Hence S is equal to V1 V2 V3 is linearly independent, and hence S spans R3. Okay, so in that case again I explain this theorem. It's very important to solve some example, this type of example, that if your dimension of V is equal to n and S contains exactly n elements, then S is basis for V if and only if S is linearly independent or S spans V. So in that case these three statements are equivalent: S is linearly independent and S spans V. Whenever your dimension of the vector space and the number of elements are in the set both are same, in that case. Okay, so next example, question 3c. Let set of 2 cross 2 matrix have the inner product, where inner product we defined with this manner: trace of A transpose into B, find the cosine of the angle between A and B, where A is equal to 2 6 1 minus 3 and B is equal to 3 2 1 0. Now what is the formula for to find the cosine of the angle? Cosine cos theta, that is equal to inner product AB upon norm A into norm B. That is the formula to find the angle between the any two vectors, right? So if cos theta is equal to inner product AB divided by norm A norm B, so in that case we can say that norm A, theta is equal to cos inverse in a inner product AB divided by norm A into norm B. Okay, so in that case, now first of all we have to find what is A transpose into B, right? So this is a A transpose into B, that is equal to 2 1 6 minus 3 3 2 1 0. How we multiply the two matrices, that you should know. Just pick up the first row of the matrix and multiply with each column. So you get 2 into 3 6 plus 1 into 1 1, so that is 7. 2 into 2 4 plus 1 into 0, that is 0, so 4. 6 into 3 18 minus 3 into 1, so 18 minus 3, that is 15, and 6 into 2 12 minus 3 into 0, that is 12. Okay, so 7 4 15 12. This is the A transpose B, and we want to find trace of A transpose into B. Now trace of means what? The sum of the principal diagonal sum of the principal elements. So that's why we take 7 plus 12, that is equal to 19, and inner product AB, that is equal to 19, right? Now also A transpose into A, that is equal to 2 1 6 minus 3 into 2 6 1 minus 3, right? A transpose into A, because of we want to find norm A. Now norm A square, we know that one formula, that norm A square is equal to inner product A with A. So if you want to find norm A, just we have to find inner product A with A and then square root of that value. So that's why we find A transpose A, that is equal to 5 9 9 45, right? And B transpose B, that is equal to, you can easily get 10 6 6 4. Okay, so norm A square is equal to inner product A with A, that is equal to trace of A transpose into A, that is equal to 5 plus 45, that is equal to 50. Okay, that is equal to 50, and norm B square is equal to inner product B with B, that is equal to trace of B transpose B, that is equal to 10 plus 4, that is equal to 14. Okay, so norm A is equal to under root 50 and norm B is equal to under root 14, correct? Now we want to find the cosine angle between these two matrices. So cos theta, here is the formula. Cos theta is equal to inner product AB divided by norm A norm B, that is equal to 19 upon 5 root 2 root 14, that is equal to 19 upon 10 root 7. Okay, so here the complete the solution of this question. This is the question number 3D. Show that V is equal to xy, where x is equal to 3y is a subspace of R2. State all possible subspace of R2. Here V is equal to xy, so x is equal to 3y. Take two elements x1 y1 and x2 y2. W is equal to x2 y2 belongs to V. Now to prove subspace, we have to prove just two conditions, that closure under addition, that is if uv belongs to V, then u plus v belongs to V, and for any alpha scalar, alpha into u belongs to V. So when we prove that u plus w, that is equal to x1 y1 plus x2 y2, that is equal to x1 plus x2 y1 plus y2 belongs to V. Now since why this element belongs to V, because it satisfied the condition, that is the coordinate of the first coordinate, that is equal to 3 into the second coordinate, that is x1 plus x2, that is equal to 3 into y1 plus y2, because of x1 is equal to 3y1 and x2 is equal to 3y2. So that's why the first condition for the subspace is also satisfied, and second condition is also satisfied. Okay, so quite easily alpha belongs to R and u is equal to x1 y1 belongs to V. So alpha into u, that is equal to alpha into x1 y1, that is equal to alpha into x1, alpha into y1 belongs to v. And since why this alpha into u belongs to v, since alpha into x1 that is equal to alpha into 3 y1 y1, that is equal to 3 into alpha y1. So here we question paper up to this question 3. Thank you.